Good afternoon. Welcome back to our Cyber Physical Systems course. And today we're going to talk about software engineering in the context of cyber physical systems and with the background that we have discussed of systems engineering. So that's what we're going to do today. And you know that a big part of this discussion is going to be related to requirements, because that's a big part of the systems engineering discipline, which I'm going to be relating to software engineering in the context of cyber physical systems. So before we launch into that, I wanted to share with you a brief YouTube video that I found. Some colleagues of mine also found that presents a very hilarious and brief, it's only like 5 minutes, but a demonstration of not only the importance but the challenge of capturing high quality requirements. So this is a dad that has two small kids, and he wants them to write a good set of requirements on how to build a peanut butter and jelly sandwich. So let's see what happens there.
You know what? I'm hungry. I could really go for a peanut butter and jelly sandwich. Do you guys think you can write down some instructions and teach me how to make a peanut butter and jelly sandwich?
Yeah. I'm done.
Step 1. Get 2 pieces of bread out. Got 'em. Get a butter knife and get some PB. Take 1 piece of bread, spread it around with the butter knife.
No, Dad, with the peanut butter.
I'm just doing what it says. It says take 1 piece of bread, spread it around with the butter knife.
Hold on.
Get some jelly, rub it on the other half of the bread.
No, Dad, open the jelly.
Well, it doesn't say to do that. Put the breads together on top of each other. Take a big bite. This doesn't taste like a peanut butter and jelly sandwich. Fail.
Yeah. Oh, yeah. Sorry, I had to make it extremely specific.
Oh, good. I'm starving. Take 2 pieces of white bread out of the bag. Take the lid off the jar of peanut butter. Get a butter knife and stick it inside of the peanut butter jar. With the knife, scoop a bit of peanut butter out of the...
That means like a lot.
A bit means a lot?
In my world.
All right. There we go.
Doing better than before, though.
Open the jelly jar. Squeeze it onto the other piece of bread.
No.
Done. Closer. Get 2 pieces bread. Get some peanut butter. Take the peanut butter knife. Open the peanut butter. Put the knife in the PB. Get some jelly. Open the jelly.
No.
Squirt the jelly onto the bread.
You're supposed to...
Take the butter knife with the peanut butter on it. Wipe it all over the piece of bread that's blank. Take the butter knife. Rub the jelly all over the piece of bread.
Oh, he's doing better.
It says all over. Put the 2 pieces on top of each other.
This is how I meant.
Take 2 pieces of white bread out of the bag. Take the lid off the jar of peanut butter. Get a butter knife and stick it inside of the peanut butter jar. With the knife, scoop some of the peanut butter out of the inside of the jar. Spread your scoop of peanut butter onto 1 of your pieces of bread with a knife.
No!
Squeeze some jelly onto the other piece of bread. Spread the jelly on the bread with the butter knife. Put your 2 pieces of bread, peanut butter and jelly sides together. Done. Get 2 pieces of bread. Get some peanut butter. Get some jelly. Open the peanut butter. Get a butter knife. Put the butter knife in the peanut butter. Take the butter knife out of the peanut butter.
You did it wrong. No.
Take 1 piece of bread and take the butter knife that has the peanut butter on it, spread it all over the top of the piece of bread.
Dad,
That's the top.
I mean the sides.
Squirt some on another piece of bread. Take the butter knife, rub it all over the top of the piece of bread.
I quit. You're not making any sense. Zari ruined it on purpose. He knows how to make one. I know, Evan. It's the joke. It's the game that we're playing. Oh.
Do you know how to eat a piece of bread? You want to take your sandwich with you?
I edited a bit.
Take 2 pieces of white bread. Take the lid off the jar of peanut butter. Get a butter knife and stick it inside the peanut butter jar. With the knife, scoop some of the peanut butter out of the inside of the jar. Spread your scoop of peanut butter onto the face of one of your pieces of bread with the knife. Squeeze some jelly onto the other piece of bread. Spread the jelly on the bread with the butter knife. Put your 2 pieces of bread, peanut butter and jelly sides together. Done.
Now eat it.
Not the best,
Well, you made it.
but
so.
I think it qualifies. That's a win.
Woohoo!
Well, exaggeration is part of making things funny, but I think it makes a point. It's not so clear how to write good requirements because there is a degree of subjectivity of what the audience is going to interpret. So one of the ingredients of writing good requirements, if there is a place for ambiguity, is to put yourself in the shoes of the audience. The other technique is not to use a natural language, so because it's subject to interpretation. So other tools like models and mathematical formulations are not subject to interpretation, so you can be more precise. So I found that video, and I thought I would share it with you guys. Okay, so let's talk about software engineering. So, because the complexity of software, the craft of developing software has actually evolved to a level of maturity where we can call it software engineering. And it basically has all the underpinnings of the engineering discipline of having a process, following certain type of rigor, and that's what we're going to be discussing today. It is an IEEE standard that dates back to 1990 with a pretty recent revision in 2011, but here are a couple of definitions by a couple of people as far as 1972. So software engineering is the application of a systematic, disciplined, quantifiable approach to the development, operation, and maintenance of software, which is any set of machine-readable instructions that directs a computer processor to perform specific operations. Then we have that software engineering is an engineering discipline that is concerned with all aspects of software production. So now the idea that software is a product, it is. It also can be a component of a larger system. And we also have that software engineering is the establishment and use of sound engineering principles in order to economically obtain software that is reliable and works efficiently on real machines. So 2 components, reliability, efficiency. So you can see a lot of the type of care-abouts that we have in, let's say, hardware engineering. So because of the complexity of software, the craft has matured, and there are schools that offer software engineering degrees, and they get accredited just like other degrees get accredited in engineering. And in our case, we do have a pretty good software track in the computer engineering program. Not so much for double E. So I think that if you're a double E thinking more about these things, it would be very beneficial, because you're not going to get a software engineering course like the computer engineering people are. So that'd be very beneficial, because there is no way of getting away from it, from software. Everything is going to have some type of software, whether you are a computer or a double E, you will have to deal with software at some level. And obviously, if you're a double E, that's not what you want to do. You'll be more on the hardware side, but you have to understand something about software development, if nothing else, to interface with your colleagues that are going to be developing software. So back in the day, as software became more complex, people started thinking that we have a software crisis. That manifested itself by the fact that frequently software projects were really never completed to the point that you could say that is done. There were a lot of ongoing maintenance, ongoing bug fixes, and the amount of time that it took to just keep going with it immensely surpassed the original amount that was budgeted and employed to write the first release to begin with. So it was really unprecedented in that no product that anybody had seen had that issue, had that problem. So some people in the industry deem this a software crisis. Also, the functionality seldomly met the requirements. It was something that was put out there, and remember that software from a craft perspective was sort of new. So very few people were good at developing software. And even though the quality output was not there, it was kind of a take it or leave it attitude, because nobody else could do it. That's not the case, of course, anymore. We have gotten a lot more discipline. And in terms of being able to develop software and going back later and looking at it and knowing what you did, it was very difficult, because, again, the complexity had grown. And software, if you think about it, in the way that we interface to the source, the product, the source code, is essentially text, mostly. So if you have a large project, tens of thousands of source code, it is very difficult to get a good visibility of the relationships and how things connect to each other, and how software uses different components and functions and loops back onto itself, and then you can have recursion and nesting of functions. It's hard to visualize. It's not something physical that you can follow a wire, or you can look at something physical. If you have thousands of lines of code, you can imagine the level of difficulty to keep it all straight, to the point that the people that wrote it came back to it and they didn't know what they did or why they did it. So that was another problem from a software engineering perspective. So again, steps were taken to kind of formalize the development of software as an engineering activity that has discipline onto it. And to that point, the people that started looking at this and crafting the software engineering as a discipline, they came up with sort of a code of ethics. And each of the professional organizations of engineering they always had a code of ethics for engineers, and there was nothing for software, but they sort of came up with these principles, with these 8 principles, so that the people developing software could attain that level of accountability, responsibility, and professionalism that was not necessarily being associated with programmers. So here's the 8 principles in several dimensions. So first, the public. Software engineers shall act consistently with the public interest. In terms of client and employer, software engineers shall act in a manner that is in the best interest of their client and employer, consistent with the public interest, again. In terms of product, software engineers shall ensure that their products are related and related modifications meet the highest professional standards possible. So that professionalism angle there. Judgment. Software engineers shall maintain integrity and independence in their professional judgment. That's a big part of being ethical, to have to essentially make the tough decisions for something that is right in his own merit. In terms of management, software engineering managers and leaders shall describe to and promote an ethical approach to the management of software development and maintenance. In terms of the profession, software engineers shall advance the integrity and reputation of the profession consistent with the public interest. In terms of colleagues, software engineers shall be fair to and supportive of their colleagues. And in terms of self, software engineers shall participate in lifelong learning. So a lot of these principles are embedded in one way or another with other principles for other engineering disciplines and codes of ethics. So that is the first 8 principles that the people interested in advancing the profession or the activity of software engineering as a profession came up with. And it can be a profession, but it's also an activity. You can be any type of engineering, and at some specific point, for some specific project, be doing software engineering. Just like you could be a systems engineering, as that's all you do, but the way that I try to relate that activity and that discipline is that you can be any type of engineer, and at some point, be doing systems engineering. So at least those two, systems engineering and software engineering, clearly they can be a profession, but it's also something that is an activity. It's a discipline, it's a philosophy, it's a way of tackling the activity of designing systems and the software associated with it. So in terms of software engineering, classically, there have been a couple of models, development models that have been used. One is the Waterfall method and also the V model. Those are 2 different models of development. They're related, but they're different. And those are in sort of the classic camp. The other, more recent camp is the Agile method, which if you look at it closely and you learn about it and appreciate it, it can be actually applied to other types of development, not just software. It has some good things embedded in it, as we'll see. So those are the 2 camps, the classic, and in there the Waterfall method and the V model, and the more recent Agile method. The V model looks like this from a software engineering perspective. And along this side, we have the development track where you start developing your software, your product, and then that software needs to run perhaps with other components, with other technologies, and you start integrating that work product to come up with the whole system solution. So you go up on that track along the integration path. So from a design perspective, which is where more of the specification happens, you are in this track. So you start doing system level specification, subsystem, and all the way down to unit testing or unit development. And that is related with what you have to integrate with other things and further validate and understand and get feedback from. So at the unit level, let's call this a macro unit or program, subsystem, and system. So the idea is that you start over here and you go down this path and then you come up the integration, and if you have good specifications, which are shown here by these correlating arrows from right to left, you have good specifications, then everything should go smoothly and you should come up and end up with the solution that your design addresses. So that's the classic V model. There is a related waterfall model, which basically also goes phase by phase, and you can loop back to a previous phase as you find and get feedback from the work being done in the different phases at the different systems of system, program, and unit levels. But the main thing of these two is that it emphasizes a lot upfront requirements definitions and also requirements analysis. And that's a big part of what we discussed when we were talking about systems engineering. It also emphasizes functional system design, which could be could have the functional specifications, the system requirements, or specification sheets. These are different terminology that is used to basically capture requirements from a functional perspective for the software. And this type of specifications are really looking at what the software does. And we're going to see that in software engineering, more than for something that is well bound like software, anything for something more than anything else, it's very important to separate the what versus the how. In hardware, it is important as well, but you have to have pretty good, pretty complex hardware for that to be felt. But for software, very quickly you can see that separating the what's versus the how has an immediate benefit. And these specifications or requirements are going to describe what the software does from a black box perspective. So we don't know what is inside the black box. We just know that at the periphery of it, from an input-output perspective of that software system, we need to see this behavior, this interaction. And those can include things like, what does the graphical user interface looks like, different screens, what is the storyboard of navigation as the software interacts with the users, and things like that. Now, more recently, with the advent of more and more graphical user interfaces, the overall work of producing good specifications for graphical user interfaces and a superset of it, which is what we would call the overall user experience, is actually a whole different discipline that gets done more separate than the actual requirements of the software from a functional perspective. So that is important as you start dealing with more advanced methods and technologies of human-machine interaction. For example, virtual reality, augmented reality. So you can no longer look at this as a part of the software requirements. You have to look at that as a system or subsystem unto itself that needs to be specified from a requirements perspective. And there are people that's all they do. They do user experience requirements, which really encompasses not only the graphical user interface, but everything else that makes the user interact with the product. So again, this system view does not describe how to achieve the work from a technical perspective. It doesn't say how it needs to be done. It concentrates on what needs to happen, not only from a functional perspective. You may bring the user experience into it, but other aspects are performance. What is the response time of the software? What type of resources does it consume? Disk space, memory, bandwidth. So those are part of that specification, because it has nothing to do with how that functionality is going to be accomplished. It has to do with the requirements from the outside looking in to the software, and also from a black box perspective, from the software looking out to how the user or users or the user community is going to interact with the software. Additional metrics can also encompass things like reliability related, robustness. What happens, how does it react to failures? How does it fail in a gracious manner, in a safe manner? What type of fault tolerance is required for the software? Also, what happens during installation, and what is the update capability of the software? These are things that can be specified as part of the specifications of what the software needs to do, know how it's going to be accomplished, and even what type of different platforms are going to be supported. So these are different examples, not a exhaustive list. By no means it is an exhaustive list, but it gives you some idea. We have not talked about in this list of what are the different technologies that could be used, how the software is going to be implemented, just what are the things and aspects and metrics that the software needs to have. Then you can go into the next step, at least from the V model and waterfall model perspective. Once you have all these requirements, because we're going to see that the Agile method is a little bit different. Once you have all these requirements, you can go into the next phase where you can actually start worrying about how to bring this software to life. And as you go through that, you can start doing the actual technical system design, also called software architecture, where you can start to think about how to implement the software from a technical perspective. So examples of that is, what is the language that should be used? And this is something that you're going to encounter as you go into the workforce, is that from a computer and electrical engineering perspective, you're going to be associated and you're going to be working with some type of embedded system. There is no doubt that you're going to be doing that. And for many, many years, there is a huge install base of C and C++ code for embedded system and real-time systems. But now there is a challenger to that. Anybody knows what that is? Python, right? And we see Python being used for memory-intensive applications. So it may be that part of that specification is, it needs to use this language or this other one, because we're having more and more choices of languages. But that's part of the how that you can start working on after you have a strong understanding of what the software needs to do. Other thing is actual class diagrams or UML representations and database schemas. What is the functionality of the database that is going to support a specific functionality of the software? How do you code the schema for that? If you're talking about user interface, you could start specifying that in cascaded style sheets, in different tools. You can start doing that at this point. Then you can also start specifying the level of maintainability that you're going to implement, how you're going to test, and what happens when the software needs to be modified. What interfaces the software must have, not only with the external world and with specific hardware components, but also interfaces between modules of the software. Software also has interfaces, and there are some standardization in those interfaces for software, but they are not as standardized as hardware because it's relatively newer. Applying this rigor of development for software, which one part of that is standard interfaces, is newer than for hardware. So you can, again, start expressing the elements of how the software is going to be developed, including what artifacts you may use, such as dynamic link libraries, what server type you need, and what is going to be required to be installed to run the software. So it gets more specific, but from a waterfall and V-model perspective, only after you have a good grasp of the requirements from a user perspective. So during the implementation part, after the modules have been tested and you start going through that integration path, you start doing the actual functional testing of the different modules as you integrate them, and eventually you do validation or acceptance testing. So I alluded to this in a previous lecture, but here it becomes very important to make the distinction between validation and verification. Validation supersedes verification. Validation says or answers the question, did we do the right things to meet the customer requirements, to meet what the customer wanted? So that the perspective is customer-centric. Did we do the right things? Verification refers and answers the question of, did we do something properly? Even if it was the wrong thing. So you can have a specification that it captures poorly what needs to be done to satisfy and meet the customer requirements, and you can have that specification and someone designs to that specification and you verify against the specification and that verification exercise will be successful because you did what the spec said that needed to be done. Now the validation is that when we release that product, does it behave, does it conform, does it do what the customer needed, what the customer wanted, and what the customer is paying for? That's the validation part, which is called also acceptance testing. So those are two very different things. We want both. First, we want to capture the requirements, so we do the right things, and then we need to do those things right, which is the verification part. Now next, I want to shift gears and talk about agile development for a few slides, because it's really a different way of approaching, and it does deviate from the rigor of the waterfall and the V models. So it started with the introduction of the Manifesto for Agile Software Development that was introduced in 2001. So some of the authors of this document and way of thinking formed the Agile Alliance, which was is a non-profit organization that promotes software development according to this manifesto's values and principles. So when Jim Highsmith introduced the manifesto on behalf of the Agile Alliance, he said this: the Agile movement is not anti-methodology. In fact, many of us want to restore credibility to the word methodology. We want to restore a balance. We embrace modeling, but not in order to file some diagram in a dusty corporate repository. We embrace documentation, but not hundreds of pages of never maintained and rarely used tomes. We plan, but recognize the limits of planning in a turbulent environment. Those who would brand proponents of extreme programming or Scrum or any other agile methodologies as hackers are ignorant of both the methodologies and the original definition of the term hacker. So, as it happened, when change is introduced, the pendulum tends to swing to the opposite, to the extremes. And extremes are not good. Balance is what gets you there. So if you imagine, as I was saying, that people were declaring a software crisis, they started putting methodology in place and models like the V model and the Waterfall model. The pendulum swung to the point that now we cannot do anything until we have an ironclad spec, and we cannot change the spec. And if we change the spec, that means we go back to square one and start the clock counting on the schedule and things like that. So it became very rigid. But reality doesn't work that way. The reality is somewhere in the middle. So a response to that was, well, now let's bring some flexibility in that very rigid process that had emerged from the disarray and the crisis that had been declared at the beginning. So that's what the agile development tries to do, or that way of thinking tries to do. So less emphasis is put on the details because it is recognized that sometimes you don't know all the details. And if you wait to know the details, then you don't get anything done. So how can we, instead of just sitting and waiting for specifications that are 100% complete, have just an overview of what modules do so you can start going? And then you start iterating through that development process in a very fast way, which are called sprints. And instead of doing something and waiting to get tested downstream, or if you are downstream, waiting to get something from the previous workstation or the previous work product, all the software is always being tested in its entirety. So you always have some type of version of working software product all the time. So there is no halfway product. And it may not do all the things, and it may not have all the features implemented, but it is a complete product in the sense that it runs. It runs. You're not just not doing anything and just doing functions or sub-modules or modules forever, and no one is really trying to integrate that and see if they talk to each other, at least in some manner, to see the problems ahead of time. So that's an important part of the agile way of developing software. What you're doing all the time relies on the state of knowledge of the team at the time. So it requires a lot of close interaction of the teams working in the software development project. A lot of communication, frequent and close communication. Out of that came a 12 principles of the Agile software development practice that has been launched by the Alliance that supplement the manifesto, and they are as follows. Number one, the highest priority is to satisfy the customer through early and continuous delivery of valuable software. So early and continuous of something that is valuable. You keep adding as more understanding of that state of knowledge is augmented. Changes are welcome. So welcome changing requirements, even late in development. Agile processes harness change for the customer's competitive advantage. So another way of looking at it, instead of resisting change because they're going to happen, it is part of life of technical development. Instead of resisting that, embracing it and trying to make the way that the developers deal with the changes in requirements as a competitive advantage for themselves as developers and their customer. Number three, delivering working software frequently from a couple of weeks to a couple of months with a preference to the shorter time scale. So again, short iterations, making sure that the feedback goes quickly to the developers and that the process is expedited. Number four, business people and developers must work together daily throughout the project. So bringing that business view into the development gives the developers and makes them close stakeholders of how the customer feels, the level of appreciation that the customer feels, the financial incentives that are associated with the project. So they just don't see that this as a pure software project, but also is a business. We're doing something useful. It has a financial value associated with it. And that comes from close collaboration and mutual respect between the business side of the enterprise and the technical side. Number five, build projects around motivated individuals. Give them the environment and support what they need and trust them to get the job done. So that's a philosophy of management of empowerment, giving people the infrastructure and the tools and the training and whatever they need, and expecting and hoping that they're motivated and they will reach out and have the initiative to basically bring up any difficulty that they are going through. If they feel that they're going to get that support, then they will do that. So it's a level of openness between whoever maintains that infrastructure, let's call it management, and the contributors of the technical work product. Number 6, the most efficient and effective method of conveying information to and within a development team is face-to-face conversation. So, close communication, and nothing really can replace face-to-face communication. Text is very far removed. 90% of communication is nonverbal. So at least, and you don't get that through a phone call, so at least video conferences, I know in my own experience, they work well. Sometimes people cannot be in the same room, but there is very good video conference technology. I'm a big fan of video conferencing when I need to work with people that are not on the same room with me. And I do find that you get a lot of what you get from being in the same room via good video conferencing products like Zoom. We use Zoom all the time. Working software is the primary measure of progress. So how do you know that you're making progress? Will the software work? Do you have something? And what you did last week, does it have additional features this week? If not, then progress is not being made. Because even though the number of features that are coming up may be in flux, at some point it's going to get stable. And if you have this methodology of bringing and folding these changes in a quick way, once you start getting a stabilization of the features, then you almost have a product. And you have been testing all the time. You've always been getting something out of the cycle. So that's how you would measure progress. Do you have working software that is evolving as the feature sets are evolving? Number 8, Agile processes promote sustainable development. The sponsors, developers, and users should be able to maintain a constant pace indefinitely. So again, that rhythm of development, trying to fold new requirements in the development and the release of software as quickly as is possible. Number 9, continuous attention to technical excellence and good design enhances agility. True. So if people like what they're doing and they are technically competent and they like what they do and they pay attention to detail, then you make fewer mistakes and you can move faster. So that's very clear. Number 10, simplicity, the art of maximizing the amount of work not done, is essential. So simplicity, so you do less, not that you're going to work less, you do less for a specific solution as long as you meet the requirements, because then you can do something else or you can go even faster. So simplicity is a way of fostering agility. Number 11, the best architectures, requirements, and designs emerge from self-organizing teams. So it fosters self-organizing teams instead of being driven tops down, essentially the management putting the talent together and let the teams kind of organize in different roles and distribute the work in a way that emerges organically from the chemistry, the interactions, and relationships of the team members. And then, number 11, about continuous improvement. At regular intervals, the team reflects on how to become more effective, then tunes and adjusts its behavior accordingly. And if you have an easy way of measuring or of assessing the level of quality with which you are working, which in this case we're calling for working software, very simple, very quantifiable, then you can start sort of peeling the onion and say, how can we do this better? And if we didn't accomplish this, why didn't we do it? And what were the ingredients that would have led to us performing better? So you can start that forensic analysis and going back to the point that you can identify very relatively easily what are the things that you must improve to become better. So it also, the Agile methodology also fosters a philosophy of continuous improvement, which is very important. All right, so with that, I'm going to stop here for today, and next time, on Wednesday, we are going to discuss how we put all this together, systems engineering, cyber-physical system representations, and software engineering, to come up with requirements in software design for cyber-physical systems. So thank you very much, and I'll see you on Wednesday. Thanks.